Hello, welcome to Wireless Communications. So basically, this course starts with modeling the wireless channel, and this is a big topic that is worth of a full course on its own. But here we will basically try to focus on the most important things that will be relevant to the subsequent parts of the course. And most of these things actually will be things that you will see in the literature when you read papers. Okay, so basically, wireless communications is broadcast by nature. So you transmit your signal, and there is an antenna, and you basically transmit from the antenna. The signal comes from the antenna in all directions, or if it's a directive or high gain antenna, the transmitted power will be focused in a particular direction. Now, as the signal basically propagates away from the transmit antenna to some receiver here, there is something called path loss, okay, which means that the power, okay, the received power, if you put some receiver, okay, at some distance from the transmitter, the received power will decay with the distance. Okay, and the reason is that, you know, you can imagine that there is a transmitter in free space, and suppose that it is isotropic or omnidirectional, and basically for this transmitter, the power transmitted is distributed over a sphere, right? So at distance d, it's distributed over a sphere with surface area 4 pi d squared. Okay, and so if you put, to put it this way, the power the power density, the power per unit area at distance d will decay as d squared. So you put a receiver basically at distance d, and you will get some power. If you basically increase d, this power will get smaller. Okay, and of course, like, wireless systems do not operate in free space. Okay, there are all sorts of things. There is the ground, buildings, people, vehicles, and so on. And so propagation in the wireless environment is very complicated, but we can abstract things using this simple formula that the received power is some constant. Okay, so it is some constant multiplied by the transmitted power, and then you divide by the separation between the transmitter and receiver raised to some power beta. Okay, so in free space, again, this beta will be equal to 2, but again, the wireless environment is much more complicated, and so there is a path loss exponent, beta, typically in the range from 2 to 6. And you can obtain this beta by doing measurements. So like in homework 2, you'll solve a problem in which, like, I give you the measured power at basically this some specific distances from the transmitter, and then you can basically do interpolation or fitting and get a good estimate for this path loss exponent that is beta. Okay, so this is like the most widely used path loss law. The power decays as r to the beta, where beta is some number. Now, mathematically speaking, I mean, sometimes if you like use this path loss model in your work, sometimes you will face mathematical troubles because as r tends to 0, so right here you have r, it's in the denominator. If it tends to 0, basically this thing explodes. And so in some studies, basically you will have to deal with this sometimes by abandoning this law, and sometimes you assume the power rather than that it's basically decreasing with distance like this. Sometimes you can just assume that it's like constant or almost constant for small distances to the transmitter, and then it starts its decay, and so on and so forth. There are so many of those path loss models. They will not be of interest to us in the first part of the course. We will come back to them when we start the chapter on stochastic geometry. Okay, so but this is like what we need for now. And of course, like there is a big story behind it. So what is K? And you saw K, for example, is related to the antennas. Okay, to the antenna gain, effective area, and so on. But again, for our purposes, we will just have it at a constant. Again, a constant that you can determine via doing measurements. Now, there is something. So we have Pathloss, then we have shadowing. And shadowing means that basically sometimes, or actually many times, especially if you are in a dense urban environment, you don't actually have a line of sight between yourself and the base station or the transmitter. Sometimes between the transmitter and receiver are many obstacles, perhaps buildings, walls, thick walls, and so on. So basically, so maybe there is this transmitter here, and this is the receiver, but between them, you have this thick wall, and basically the signal will have to penetrate through this basically wall. And so you have losses now, additional losses, because part of the signal will be actually be reflected or scattered, and some fraction will come out here. Okay, and so shadowing gives you like an additional loss. So it's not now a loss because of the distance. It's loss because like there is something, or there are many things between the transmitter and receiver. Now, how do we account for shadowing? Well, again, the simplest thing, which will be useful to us, is that you say that the received power, it's same as before. So it is some constant times the transmitted power divided by the distance raised to beta, but then you add a random variable. So here you model shadowing by multiplying the received power by a random variable, which will account for basically those obstacles. Because of course, sometimes some users will be behind, obstacles. Some users will not be, or basically, there may be some users with line of sight, others without line of sight, but actually there is like little attenuation caused by the obstacles. I mean, obstacles differ. I mean, for example, a wall will block a fraction of the electromagnetic energy, depends on its composition and its thickness and so on. Okay. So what we tend to do is that we model this shadowing as a random variable again that is multiplied by basically what you get due to Pathloss. And this random variable is typically written in this way. So we typically write it as 10 to the zeta over 10. So we don't like say that this is a random variable x. We write it in this form, which is 10 to the zeta over 10. Okay. So zeta will be our random variable, and the actual random variable that is multiplied by basically by kb transmitted over r to the beta will be 10 to the zeta over 10. And the most basically famous model for shadowing is log normal shadowing. And log normal shadowing simply means that we model this zeta here as a Gaussian random variable. Okay, so it is Gaussian, zero mean, with some variance that is equal to sigma squared. Okay, and so writing it this way, if you express your received power in decibel, okay, so in decibel it means that you take basically this thing, you take its logarithm to the base 10, and then you multiply by 10. So there will be terms here, and then there will be. So if you take this guy, take its logarithm to the base 10, and then you multiply by 10, you just get zeta. Okay, so so it is written like this again, so that if again you measure your powers in dB, then basically the shadowing effect will be an additive random variable. Okay, and again typically it's taken as a zero mean Gaussian with some variance, and this variance again is one of the parameters like beta and k that can be obtained using measurements and fitting. Okay, so this is basically what I was saying here, that the received power in dB will have this guy as an additive guy. But power, basically on a linear scale, shadowing is basically multiplied. The shadowing parameter is multiplied, and it's typically written in this form. So two things: Pathloss, shadowing. The third guy is multipath, and this will be actually our focus. So here we will go deep into multipath. For the first two guys, you can read the relevant chapters in the wireless communications book by Goldsmith. Again, I will focus here on multipath. It will take us some time, and here I will provide, the necessary details. Okay. Okay. So multipath, from its name, multi-path. So multiple path. So it means that whenever you have a transmitter, okay, and you have a receiver, okay, then the signal going from the transmitter to the receiver, there may be a line of sight or not. Okay, so this is a line of sight, a direct path between the transmitter and receiver, but then there may be an obstacle here, a building or something, and then part of the signal will be basically reflected off this wall, come here, and then perhaps, there is another obstacle there, and so on and so forth. So typically what the receiver gets is multiple copies of the transmitted signal. Okay, so that's multi-path, multiple copies. And now those paths, they have different lengths. Okay, and hence electromagnetic wave basically it does not propagate with infinite speed. So we have the speed of light. So basically there is a delay along each path, and the delay is the length of the path divided by c approximately. Okay, and so basically those replicas will be received with delays relative to one another. Okay, so suppose, I mean, it's not an experiment that you can do. If you transmit a Dirac delta, okay, in practice you can do something very close, but let's just talk mathematically. If you transmit a Dirac delta, then in the receiver, so basically this is time, and the received signal will be after a while, because there is a minimum distance. So along the line of sight, there is a minimum distance between the transmitter and receiver. So after so if this is 0, then after some time you will get the Dirac delta, okay, with a certain amplitude, and then after a while you get another one, and then another one, and then another one. Again, those comes from the other, the other path. Okay, so you get something like this. Now, what is the problem with multipath? Well, I mean, basically, if you transmit just sinusoidal signals, okay, we do not do this in communication systems, but if you transmit basically a sinusoidal wave, now suppose that you get another version of this sinusoidal wave that is shifted by pi/2. Okay, so the other wave comes like this. Now in the receiver, these two guys will cancel. Okay, so the multiple paths interfere with one another and they may cancel. Okay, so we have this cancellation due to the signals being out of phase. Okay, so receiving multiple copies of the transmitted signal is not as easy. It's not like something good. I mean, because it's like you are collecting more energy, or like more of the transmit. Actually, the received replicas may annoy one another in some way. Okay, and so you may get degraded performance. And one of our first tasks in this course is actually to investigate this. Okay, and of course, like we cannot just do things in an ad hoc way like this. We need like to have a model, a justified model, and basically do some mathematical analysis. Okay, so let's delve into basically the business of multipath. So you transmit a signal, and the transmitted signal is S of t, so that's the baseband transmitted signal. You multiply by e to the I 2 pi f carrier t, and then you take the real part. So this is the transmitted signal. And so, of course, I mean, you do not transmit complex signals from an antenna, right? You transmit a real valued signal. So we say that our baseband signal is complex valued. What we mean in practice is basically that our transmitted signal, it has a real part and it has an imaginary part, We multiply the real part by cosine, we multiply the imaginary part by sine, and then we have a minus between them. And this is actually what is transmitted from the antenna. Okay, so saying that our signals are complex, like, so for example, S of t may be a QAM symbol, so perhaps this may be a QAM symbol plus a pulse shape. Okay, and again, it's complex, real part, imaginary part. This is like a model. Again, what we do is that we take the real part times cosine, the imaginary part times sine, and we have a minus. And this is a real valued signal that is emitted from the antenna. Now you receive the signal, okay, and when you receive the signal, basically you get the signal through a number of paths. So I will write down the received signal as a summation. So this summation is because we don't just receive one copy. Okay, so we can receive the signal along the line of sight. Then, it can come from several other paths. So we have a summation, and each received signal will be multiplied by a complex amplitude. Okay, so this gives you, because like when the electromagnetic wave is scattered off some surface or some object, basically, its amplitude will change. It will exhibit a change in its magnitude and the phase. And so we will model this as each path having its own complex gain. And then we have basically this factor here and this. So this is S of t minus this quantity tau bar of nt. Okay, so this n is the index it's an index over the path. Okay. And this is the delay. This is the delay, okay? But I'm writing the delay in a way that may seem like awkward. It's like a function of time, and that's true, and I will talk about this shortly. Now you can think of it like t minus delay of nth path. Okay, so your signal is delayed, and then it gets this factor here. Now, how do we basically get this factor? That's a homework problem in basically homework 1. It's here we will always assume conceptually at least that we are using the IQ receiver. So you receive your signal, you have a low noise amplifier, and then you take your signal. So your receiver. So like in the transmitter, you multiply by cosine and sine. In the receiver, you basically take your signal, you divide it into the in-phase branch and the quadrature branch, and basically you multiply by cosine, multiply by sine, then you do low-pass filtering. Perhaps you do something fanciful like matched filtering, and then you sample. If you are basically, and modern receivers are mostly digital, so you sample, and this is basically your received signal. Okay. And so if you analyze an idealized version of the system, you will find that it will give you this result. So it's a straightforward problem in homework 1. And basically what you get are two components, right, from the in-phase branch and the quadrature branch. And hence, you can also think of the received signal or the signal in a receiver of a communication system as complex, right? Because if you have two quantities, you can think of them as the real and imaginary parts of some complex number. Okay, and so we will always do this. Okay, so I will, here it's basically will do complex. I will just assume that everything is complex. Again, on the transmit side, typically we use two-dimensional constellations like QAM. Binary BSK is not complex, but you can think of it as complex. And on the receive side, again, it's the IQ receiver. IQ receiver is basically what is like implicit in whatever I am writing down. And this is again your signal. So it is like a amplitude gain, then you have exponential minus 2 pi f carrier. This is the carrier frequency, and then a delay, okay, and then st minus the delay. And you need like to decipher this thing. Delay as a function of time. Well, remember, basically wireless systems have to deal with mobility. Okay, and so mobility means that things do not remain stationary. Things change, vary over time. Okay, so this is basically the bulk delay, and it will be our here now. This is like an illustration. You have a transmitter, and basically here is your receiver. and you get your signal. It is reflected, is scattered, and diffracted. All these things that you can study in a course on like wave propagation. For us, we will focus on the received signal itself, knowing that it is received from multiple paths, coming from multiple directions, and so on. Okay, so let's now talk about the delay. So the delay, I will, so this is n, again the index n, it means that I'm focusing now on one of the paths. Okay, so let's say that you focus on this path. So this is one of them, you go and hit this scatterer here, and then you come here. Okay, so we are focusing on one of the path, the nth path. Okay, so that's not an issue, but the issue is basically that we have a delay that depends on time. So what is the definition of this thing? Tau bar of t is the delay of the signal received at the time t. Okay, so at time t there is a received signal, okay, in the receiver. Okay, so this is the delay of that signal. In other words, that the signal received at time t, it comes with a delay equal to t bar of t. So it means that the signal received at time t is transmitted at time t minus tau bar of t. Okay, so that's the definition. So basically the delay at time t is the delay of the signal received exactly at time t, which means that the signal was transmitted. So it's received at time t, and the delay is tau of t, so it is transmitted at t minus tau of t. And we make things a function of time because delays change with time. Why? Because basically these guys are moving. Typically those guys will be moving, and if they are moving, then the path length are changing, and because they are changing, the delay will change, and so basically the delay itself is indeed a function of time. Okay, any questions? Okay, so now again we will account for mobility, and we need like a simple model. I mean, we want something that is tractable. So suppose that r of t is the distance between the transmitter and receiver at time t. And so what is the delay? So the delay, you take the distance and you divide by the speed of propagation. Okay. And so here I will write that the delay at time t, again by definition, it's by how we define it. The delay at time t, it's the delay of the signal received at time t. So the signal was transmitted at time t minus tau of t. Okay. So basically the delay at time t is the distance or the separation between the transmitter and receiver at time t minus tau of t. Okay. And then you divide by c, which is again the speed of propagation. That's a scary formula here. And so you have here the delay as a function of time, and it's inside. And so what we will do now is basically a succession of assumptions so that we get a tractable model, because this is extremely difficult, perhaps impossible to handle. So to get something that is manageable, we need basically to simplify this thing. And to simplify, we need to do basically an array of reasonable assumptions, as you will see. Okay. So you take the expression, differentiate it once with respect to time, and when you differentiate it once with respect to time, basically this guy becomes its derivative, and then we have the derivative of r, and when you apply the chain rule, basically you need to differentiate what is inside here, and so t becomes, so d by dt, t becomes 1, and then this is our function again, the delay is a function of time, it gives you t dot. Okay? And so this is basically the chain rule, nothing else. Now we need to talk about r dot. So r dot is the rate of change of distance, the rate of change of separation. So here r dot is something related to speed, is something related to velocity. Okay, and so what should be this thing? let's suppose that basically this is the transmitter and this is the receiver, and there is a large separation between them. Okay. So this is the transmitter, and suppose that the receiver. Suppose that the receiver is moving in this direction. So it moves with speed v in this direction. Okay, this blue direction. Okay. And so in a small time delta t, basically if the receiver starts here, it will end up there, and it will move a distance v delta t. Okay. So again, here is the transmitter. Here is the line connecting the transmitter and the receiver. Suppose that the receiver is moving, okay, it's moving with speed v, and it's making an angle theta n, and in a very short period of time, delta t, the receiver will be here. It will travel a distance which is v delta t. And so theta, again, is the angle between basically the line connecting the transmitter and the initial position of the receiver, and basically this line segment here giving you the path of motion of the receiver. Okay. Now, we will assume that basically the speed is constant. So I will not use v of t. Okay. So this is the first one of the basically assumptions made to make our life easy. So we will ignore acceleration. Okay, so acceleration effects are ignored. We will assume that basically in our operation, and given the expected values of acceleration of the moving objects in the wireless system, that actually acceleration is something that we can ignore. So over a short period of time, again, you can assume that the object, or here the receiver, is moving with a constant speed. So this is very nice, again, because now v, it's not, or it does not depend. It does not depend on time, and this will simplify things a lot. Okay. Now we want r dot. So basically, the objective here is to approximate r dot. Remember, we wrote down an expression for the delay. We took the first derivative with respect to time. We applied the chain rule, but we need the derivative of r. So we want something here. We can get it from here. Okay, so well, you can get r dot by taking the new distance. So you can take the change in distance, right? R dot change in distance over delta t, and take the limit as delta t gets very, very small. Okay, so basically this is the separation between the transmitter and receiver. Now it becomes this along this gray line. Okay, so what is the length of this guy? What is the length of this guy? Well, I mean, if you want to write it exactly, I mean, it's annoying because you will have like to apply the cosine rule and say that this new distance squared is the old distance squared plus v squared delta t squared, and then minus 2, you multiply the length and you multiply by cosine the angle. And so if you want the distance, you take the square root. It's messy. It's messy, okay? So here is another approximation. What we will do is that we will say that given the separation between the transmitter and receiver, this angle is very small, and approximately this gray guy is like this, the distance from here to this point here. Okay? So it's an approximation. It is an approximation, and basically this approximation will yield a very basically simple formula. So let's see why. Let's take basically the projection of this segment over this line here. Okay, so this will be, so what is this separation? It is, so this is a right triangle, right? And this is v delta t, this is theta of n, and so this guy will be v delta t cosine theta of n, right? And so you will say that the change So now we are saying, we are taking that this is approximately equal to this, and so the original length was all this black line. So now the change in distance is approximately this guy, and it's with a minus sign because in my drawing I'm assuming that the receiver is moving in the direction of the transmitter, so the distance between the transmitter and receiver is getting smaller. Okay, of course I could have do it the other way. Okay, but here in my case I will write minus v delta t cosine theta n. Okay, and it's approximately to avoid the use of the cosine rule, which will give you square root of something. I mean, now this is very nice. Now you take delta r over delta t, it's approximately minus v cosine theta n. And so basically the derivative is minus v cosine theta n. And remember that we will assume actually that theta and v do not depend on time. We will assume that both do not depend on time, so that's good, right? Because now if we go back to our first derivative, now this thing here will be replaced by constants, things that do not depend on time. Okay, so keep track of the approximations we are making. So we are assuming that during motion this angle is fixed, v is fixed. Okay, and we are assuming that basically the separation between the transmitter and receiver is very large, so that you can apply this geometric approximation. Any questions? Okay, so here is like a recap of what happened on the previous pages. So this is the first derivative of the delay with respect to time. Don't forget what this guy is. So this is the delay of the signal received at time t, and so it means that the signal was transmitted at t minus tau of t, and so hence this formula that it depends on the separation, not at time t, but at the time of transmission, which is t minus tau of t. And then we took the first derivative of both sides, and we invoked a bunch of approximations, and now we have this result here. We can now you can see again we have no time dependence here, and we can rewrite the equation basically to get a formula for the first derivative of the delay with respect to time. Okay, so you can just rearrange things, simple algebra, and the delay now can be written. It's like a constant now. Okay, sorry, the derivative of the delay is like a constant now. Okay, so our approximations will lead to the first derivative being equal to minus cosine theta n over c over 1 minus v cosine theta n over c, and again no time dependence for v by assumption, no time dependence for theta by assumption. Okay. So now the delay as a function of time is like sort of a linear function, right? So if the first derivative is like a constant under our assumptions, it's like the delay itself like sort of changes linearly with time. And so what we'll do is that we will write down the first degree Taylor polynomial for this function. Right? So of course, at the moment I took the first derivative, I'm assuming that this function is differentiable. Okay, and hence it is differentiable. I can write down this first degree Taylor polynomial. So at time t, so the delay at time t is the delay at some arbitrary time tau of n, and then plus the first derivative evaluated at a point between t and tau of n, okay, and then you multiply by t minus tau of n. The good news, so again, like if for a general function, this thing here will depend on t, but by our assumptions, the first derivative is independent of t. Okay, so that's the trick. So now this first derivative here, okay, it's constant regardless of the time instant at which you evaluate it, and so we can just replace it by its formula. Okay, and so tau of t is tau at some time instant tau n minus this quantity t minus tau n. And so you can see now that the delay is modeled now as a linear function of time. Okay. And now what we'll do is, something. So this is a constant. Okay, so tau of n is a constant. Tau borrow of tau of n is some constant. Okay, and so the Taylor approximation for a function that is differentiable once, you know, you can choose this guy to be anything convenient, right? So when you do Taylor series, right? So you do what, like you expand about 0 or 1 or what the point of expansion is basically whatever is convenient. So what we will do is that we will choose basically tau of n, this constant tau of n, to be a fixed point of this function tau bar. Okay, so I choose tau of n such that tau bar of tau of n is equal to tau of n. And you may wonder, perhaps we cannot do this, and so this will be this is nonsense. Okay, so if I give you a function f of x, okay, and tell you, find x such that f of x is equal to x, okay, perhaps there is no solution to this equation, right? But actually we have. Okay, so you can show that actually in our case here we have. Okay, so if you want tau bar of n evaluated at tau n to be equal to tau n, okay, this is what we want. Okay, then go to the expression for tau bar and basically replace tau bar of t by tau bar of tau of n. And now, by design, we want basically these two things to exist, to be the same. And so this will be r of tau n minus tau m, which is r of 0 over c. So in fact, there is a tau n that actually gives you this, which is like sort of the initial distance divided by c. Okay. The most important thing is basically that we will have a constant here. To match this constant there, this will make the following mathematics basically sort of nicer. Oh, okay. So after this, after those assumptions, basically we have this is the expression for the delay as a function of time. So it's a linear function of time. It depends on tau of n. Note that tau of n without the bar is a constant. And so basically, we will end up using tau of n as a proxy for the delay. So as you will see in several, in the coming minutes, basically, dealing with the delay that is time dependent is like very tough. And so basically, we will use actually tau of n in place of tau of t. And so, like, we will talk about, the receiver getting signals with delays 80 nanoseconds, 120 nanoseconds. We will talk in terms of fixed delays, despite the fact that, like, whenever there is mobility, actually everything is changing with time. Okay, but again, doing things like this would be very difficult. Perhaps impossible, and so we will just go for this approach. So later, basically, tau of n will be our hero, and it's just a constant, as we will see, but we are not done yet. Okay, so this is the expression for tau bar. This is t minus tau bar, because basically our received signal depends on this. Remember, there was, in the expression for the received signal, there was s of t minus tau bar n of t, and so I just basically t minus this quantity here. And because now this constant is chosen to match this one, we have this nice expression. Basically, t minus the delay will be a constant multiplied by t minus the delay, and basically this constant here is 1 over 1 minus phi cosine theta over c. Okay, so this factor A, I mean, we won't like to sort of chat a bit about it, because this will affect, the coming discussion. So what do you think about A? Well, if we are talking about like wireless communication in air, right? So the speed of propagation is about the speed of electromagnetic wave propagation in free space, and so this is c, this big number, 3 × 10⁸ meter per second, and v is the speed, by which like a terminal, the receiver in our case here, will move, and typically v over c is a tiny quantity. It's very, very small, right? Because the speed of light is huge relative to the speed of things moving in a wireless environment. So v over c is very, very tiny. And so basically this quantity A is close to 1. So if you want to think about A, It is very close to 1. Note that my story here will differ if we are talking about other systems. Suppose that you have a system in which you are using not electromagnetic waves but acoustic waves for communications. So the speed of propagation of acoustic waves is different. It's much, much smaller than the speed of propagation of electromagnetic waves. Okay, and so if you are doing basically transmission using acoustic waves, okay, then you need to, maybe what I'm saying now will not be applicable. So I will rely heavily on this fact that we are assuming propagation in air of electromagnetic waves, not acoustic waves, and hence C is much, much greater than V, and A is close to 1. Is A greater than 1 or less than 1? This will depend on the angle theta, right? So basically, remember my drawing is that there is this, so this is the receiver is moving like this, the transmitter is somewhere here, and this is theta n. Well, if theta n is between 0 and pi over 2, then basically the cosine is positive, and you have 1 minus in the denominator, so A will be greater than 1. If theta n is exactly 90 degrees, then basically this term here will be 0 and A will be equal to 1. And if the basically theta n is an obtuse angle, between pi over 2 and pi, then cosine theta n will be negative, and this will be 1 over 1 plus something, and A will be less than 1. Okay, but in all cases, because C is much, much larger than V, A is very close to 1. Again, depending on the angle, it will be basically slightly higher than 1, slightly less than 1, or exactly 1 in the case that theta is exactly equal to 90 degrees. Any question? Okay, so this is what we have right now. Okay, so the formulas, the approximate formulas for the delay. And now we go back to our received signal, which is this thing. And let's now make use of our approximations. And so we will plug in. So we'll take the formulas for tau bar and t minus tau bar of t, and we just plug them in. And so here's what we get. We will get here a constant phase factor that depends on Fc and A and tau n. And so, typically we will basically take this, phase factor. So alpha n itself is magnitude alpha n e to some angle of alpha n. And so basically, if this guy, does not depend on time, we can just join it to basically this angle of alpha n. And we are left with basically those expressions. This is the most important part. So now, under our assumptions, okay, so we ignore acceleration. We assume that, if the terminal is moving, it's moving in some given direction with some constant speed. Okay, we are assuming that basically, that the transmitter is very far from the receiver and so on. Under those assumptions, we get a time-scaled version of the transmitted signal. So transmitted signal, you transmit S of t. This is the baseband transmitted signal before upconversion. Now what you receive under our assumption is the following. You receive A of t minus tau n. So it's a signal to which basically two operations had occurred, right? So there is a delay. Now it's a delay with a constant. So now with our assumptions, you can think of the signal as delayed with a constant value, and it's scaled, because A may, it can be greater than 1 or less than 1. So it's a time-scaled, time-shifted version of the transmitted signal. Okay, again, not so nice to handle, but what can we do? I mean, how can we push for further simplifications? So the idea now is basically to use the Fourier transform. So let's have a look at this signal in the frequency domain. Perhaps in the frequency domain, we can discover basically the feasibility of another approximation that will basically give us, sort of the most simple, non-trivial model for basically the received signal. So this is exactly what we'll do. CTFT, our friend here, so we'll take the Fourier transform, and this is very straightforward. You can take the Fourier transform, you can take it by, you can implement the integral for the Fourier transform or apply the rules for time scaling and time shifting. And basically what you get in the frequency domain, and this is not unexpected, we know from Fourier transform that basically a time scaled signal, its Fourier transform is a frequency scaled signal. Okay, and so it's like, there is no escape from this scaling. So if you have scaling in the time domain, you have scaling in the frequency domain, but let's look carefully. Okay, so now this is again the Fourier transform of the signal. Okay, so we know that, if you have a signal x of t, its CTFT is x of at, then it is big X. So this is the CTFT of small x of t, f over a, and you divide by the absolute value of a. So that's the time scaling rule for the Fourier transform. And again, like time scaling, there is a corresponding frequency scaling. So let's take the argument of the this signal, big S, which is the frequency domain signal, baseband signal. And we have formulas because we have A itself is 1 over 1 minus cosine theta n over c. So 1 over A will be 1 minus v cosine theta n over c. And so you basically get this result here. Once you use the expression for A, now you have you have frequency scaling. You can see it here. So the frequency variable is multiplied by something, but I will rewrite it without doing any approximation. So this is an equality. I will just take this term, and join it with the other term, and we have basically f alone here. Okay, so there is no approximation here. It's basically an equality, and so we have an f here, we have an f there. So we have the frequency variable multiplied by something. Okay, but here is the trick, and it's a very, very important trick. Now look at this term. It's v cosine theta n over c, and then we have f plus f carrier. Okay. Now the signal has frequency components, right? And in communications we use band limited signals, and so f basically is between minus w and w, right? So this thing here is from fc minus w to fc plus w. Okay, so f is a variable, it's the frequency variable. Okay, and again, because by design we choose our signal to be band limited. Now suppose that our signal is narrowband. Narrowband in the sense that w, the bandwidth of the signal, is much, much smaller than fc. So basically the term that you have here is f plus fc. If f lives between minus w and w, and w itself is much, much smaller than fc, then we can let go of f, because its maximum absolute value is w, and w is negligible relative to fc. And when we do this, we can cross out this f, and we get f minus v cosine theta n over c fc. So f, we have just a shift in the frequency domain, and no longer we have scaling in the frequency domain. And of course, since we got rid of frequency scaling, when we do the inverse Fourier transform and go back to the time domain, we will also have no time scaling, just a shift, as we will see. Okay, so that's a very, very important assumption. Okay, it is called the narrowband assumption, and basically, so it's called narrowband assumption, which means that fc is much, much greater than w. Note that the term narrowband, this is an overloaded term in communications. So it's used to mean a number of things. So in today's lecture, I'm using narrowband to say that we are using basically a carrier frequency for our transmitted signal that is much, much greater than the bandwidth of the transmitted signal. And so you can know that if you have a wideband system in which basically W is comparable to FC, my assumption will fail. So, we will not do this in this course, but I mean there are proposals for wideband communication systems in which you use a huge bandwidth. Basically, to describe the bandwidth as huge is meaningless unless we use a reference. So it's a huge, or basically it's so small relative to something, and here the thing is the carrier frequency. If the carrier frequency is much, much greater than the bandwidth, then we can basically invoke our assumption, and this will simplify things because we will not have time scaling now. Our received signal will just be a time shifted signal and no longer time scaled. Okay. Narrowband is used to mean other things. So perhaps in the next lecture or in the coming couple of lectures, we will use narrowband to mean a signal whose bandwidth is much smaller than the coherence bandwidth of the channel. Okay, so we'll need to do, perhaps, you know, some of you already know these things, perhaps better than me, but I will talk about it. For those who don't know, I will basically define the coherence bandwidth in, you know, coming lectures. Okay, so the word narrowband again is one of those abused terms that are used to mean several things, and you need like to use the context to understand what's it's used for. And in today, it's used to mean a signal is narrowband if the bandwidth of the signal is much, much less than the carrier frequency used in transmission. Okay, so you can eliminate this F. So you can say by, and then you can have F as just shifted, and here I used lambda as C over FC, and lambda is basically the wavelength of transmission evaluated at the carrier frequency. So lambda is just, you know, to take these two constants C and FC, and C over FC is lambda, the wavelength at the carrier frequency. Okay. So now our signal in the frequency domain is this. No frequency scaling. No frequency scaling. So you do the inverse CTFT, okay? And when you do the inverse CTFT, you will get basically, because of this exponential factor, you will get a time shift, and because of this frequency shift, you will get an exponential factor. So, okay, you know, we all know the rules of the Fourier transform. Basically, a shift in one domain means modulation or multiplication by the complex exponential in the other domain, and vice versa. If you do modulation, if you multiply by the complex exponential, you get a shift in the other domain. Okay, so again, you do this, you do the integral, you do whatever. If you take the inverse continuous time Fourier transform, you will get a signal now that is time shifted with a certain fixed delay. But since the beginning of the lecture, I'm talking about mobility and the time variations and so on. So where is the dependence on time? Otherwise, why are, you know, so we should have dependence on time. Otherwise, our approximations render the system useless because now our everything is stationary. So it turns out that basically the dependence on time will come in this term here. So rather than having a signal with a time varying delay, based on our assumptions, and our assumptions, remember, that we have lots of these, right? So constant V, right, constant theta, a carrier frequency that is basically much greater than the bandwidth, a speed that is much, much smaller than the propagation speed, and so on. Under all those assumptions, our model for the received signal will be simplified as a constant delay or shift. No longer we have this monster, okay? We now have something simpler, but we have the dependence of time in the form of this complex sinusoidal signal multiplied by the time-shifted signal. So we have e to the I 2 pi v over lambda cosine theta n of t. Okay, and v over lambda cosine theta n is the Doppler shift. This is called the Doppler shift or the Doppler frequency. Okay, so now our received signal, this is basically our friend. This is the model we will use a lot. You transmit a signal, it is received along a number of paths. For the nth path, under some assumptions, you can write down the received signal as a complex valued amplitude, as a complex sinusoidal signal, a complex exponential with a frequency fd called the Doppler frequency or the Doppler shift. And this frequency can be positive or negative, right? Because fd is v cosine theta n over lambda. Note that basically this quantity is living between minus v over lambda and v over lambda, because cosine, I mean, again, it depends on motion. If you are doing motion in the direction of the transmitter, if the distance between the transmitter and receiver is getting smaller, then theta will be an angle between 0 and 90. The cosine will be positive, and this Doppler shift will be positive. But if basically the receiver is moving away from the transmitter, so this is theta, if it is between pi over 2 and pi, then cosine will be negative. And so the Doppler shift is something that is can be positive or negative. And the physical meaning now is that it has a sign that indicates whether the distance between the transmitter and receiver is getting bigger or getting smaller. And then we have our transmitted baseband signal. Now it is shifted by constant shift. Reality is not this model. There is no model that is exactly equivalent to reality. All models are wrong, right? But it's a very, very good model, and it captures time variations, but in a simple way. Okay, this model may not be the model that you can use if you have a violation of one of our assumptions. Like what if your signal is a very, very wide band in the sense that W is actually comparable with the carrier frequency? What if you are not using electromagnetic waves, using a type of wave that propagates with the speeds comparable with the speeds of the targets of interest? Okay, so in that case, you may have to look for more sophisticated models. But for this course, this is basically our model. Any questions? Okay, and so this is like the previous slide, but of course here I added the summation to make sure that basically what I have been doing is basically the received signal along a certain path, and of course what you get is a copy of those guys. By doing summation, and this is like an assumption, let's put it explicitly here, we typically model the wireless channel as a linear system. Okay, so so even if we have several transmitters transmitting at the same time, we will just assume that the received signal is the sum of what you get from each transmitter. So so we will not basically let go of linearity. Typically, the wireless channel is linear. Not every communication channel is linear. So basically, fiber optics. Basically, sometimes you will actually need to account for their non-linear behavior. But for this course, basically, you will apply linearity and the principle of superposition liberally. Okay, so it's basically will be our game here. Okay, and some references, rather than assuming that basically you have a discrete sum, basically you assume that you have a continuous delay variable and you have an integral. You use this or you use that. Typically, it's based on convenience. Okay, so this is a very important formula at our hand. Okay. So let's see. So we start baseband. So we started with ST. So this is the complex valued baseband signal. So it went through this black box, which is the wireless channel. And so what you will get if we write things in terms of the integral, okay, is that we get S of t minus tau, alpha of tau. Okay, so here index is n. If you use discrete model, sometimes it's basically easier and better to use this one, or you can just assume that there is a variable tau and it's continuous variable, and then you have e to the minus I 2 pi f d tau. So that's the Doppler frequency or Doppler shift d tau. Suppose that v is 0 and so there is no mobility. So if v is equal to 0, then fd, which is the Doppler shift, it's directly proportional to v. If v is 0, Doppler shift is equal to 0, and basically what we get is integral s of t minus tau alpha of tau d tau. Okay, and so what is this integral? What is this integral? It's convolution integral. So if there is no mobility, then our wireless channel is like an LTI system, a linear time invariant system that is characterized by the impulse response, which is this function alpha. And to get the output, you just convolve the impulse response with the input signal. Okay? Now, if v is not equal to 0, now it's not just alpha of tau. It's alpha of tau multiplied by this exponential, which depends on time. So now if you want to write down your received signal, you write it down as integral from minus infinity to infinity, s of t minus tau, and then a function that does not just depend on tau. It depends on tau and t. Depends on two parameters. Okay, so this will be the impulse response, not of an LTI system, okay, but for an LTV system. Okay, so this is an example of a linear time varying system. Okay, and it is characterized by an impulse response that depends not just on one parameter, but actually two parameters to account for the variations in time. Okay, so h tau of t, basically it's defined as the system's output at time t in response to a Dirac delta at time t minus tau. Okay, so this is the output of the system at time t if you excite the system, if you give the system as input a Dirac delta at time t minus tau. For a time invariant system, okay, basically h of tau and t will just be a function of tau, but now it is h of tau and t. So the wireless channel is an example of a system that is linear and time varying. Okay, so before proceeding, let me try to clarify something. Okay, it's a matter of, you know, like an implicit assumption that you will encounter in this course, in the papers, and in the references, and so on. Now you have a baseband signal. So we have a communication system. So you start with your baseband signal. Do you transmit the baseband signal directly? Of course, no. What do you do? Right, so you take the signal, and then you do up conversion. Right, so you do up conversion, which means you take the real part multiplied by cosine, you take the imaginary part multiplied by minus sine. You add the two guys, and then you amplify the signal. So there is a power amplifier, and then you transmit your signal. Okay, and the power amplifier itself is not just an amplifier, it also has the characteristics of basically a band pass filter, so that it band limits your signal. Now you transmit the signal, you know, propagates through the environment, and then it is received possibly through several or many paths. And then what you do is that you take, you do the low noise amplifier conversion, and then you have the IQ receiver, right? So basically you do the down conversion to go back to baseband. Okay. So when I say the wireless system or wireless channel, sometimes, you know, you think that whenever I say this, I mean whatever is between the two antennas. Okay, so this is the wireless channel. This is the physical wireless channel between the two antennas. Okay, so this is the physical wireless channel between the transmit and receive antennas. However, when I use the term channel, and it's not me, it's basically in the literature, in the field, basically we take parts of the transmitter and the receiver and consider them as part of the channel. So I can actually imagine that my system is something like this. Okay, so we can think of this as the effective wireless channel. And we assume that its input now is basically the baseband signal. Moral of the story, that sometimes when I talk about the wireless channel, I include in the wireless channel the last stages of the transmitter, okay, and basically the front end of the receiver. Okay, so these are not just, you know, so basically typically those guys will also include analog to digital converters and digital to analog converters and perhaps other components. Okay, so here when I draw the wireless channel as an input, I put the baseband signal. But you may say, well, I mean, we do not transmit the base, we do not transmit S of t. Your very first equation was basically to take S of t multiplied by e to the I 2 pi f carrier t, and then take the real part, which is the process of up conversion, and then, okay, no problem. I mean, this is true that it's, you know, by channel, I do not really, it's not always the case. I am referring to the physical channel, you know, the physical medium between the two antennas. Okay, sometimes we take parts of the transmitter, parts of the receiver, and those are part of the channel. In the overwhelming majority of cases, actually when I say the word channel, I mean actually this green box rather than this red box here. Okay, so this is just, you know, to clarify things. Do not be obsessed, you know, with a channel being just the physical channel. Okay, we will typically assume that those components are perfect. Okay, so up conversion process is perfect, down conversion process is perfect, and so on and so forth. But then when we start our, like, the most important chapter in this course about OFDM, we will start actually to look under the hood and to investigate some of the imperfections of those guys. Okay, so we'll talk about the frequency offset problem in OFDM, and it's related basically to things happening in the processes of up conversion and down conversion and so on. But, you know, but again, otherwise we are assuming that those guys are sort of doing their stuff perfectly. But in OFDM, when we study OFDM, we will basically deal with some of the imperfections in those components. Okay. So back to our say, so the received signal is S of t minus tau. Okay, so this is the output from this after you do down conversion. So it is S of t minus tau, and then alpha of tau e to the I 2 pi f Doppler tau t tau, and then if there is Doppler is 0, which means that there is no mobility, so this guy is 1, and we just have a standard LTI system, and we have the standard convolutional formula basically to obtain the output of the wireless channel. Okay, before we proceed, let's take this alpha of tau. So remember what was alpha of tau? Alpha of tau is, for the path with characteristic delay tau, basically alpha of tau is the complex amplitude of the path. Okay, and if you take the magnitude squared of alpha of tau and then take the expectation, why take the expectation? Yes, I mean because these things are modeled as random values. Okay, so let's actually write this explicitly, that the stuff you see here, like alpha and like the angle theta in this definition, so alpha and theta are modeled as random values, okay, and with certain distributions, and we will see this in the coming lectures. Okay, so so if you take magnitude alpha of tau squared and take the expectation, okay, so this is like the average received power along the path with delay tau. Okay, again, don't forget that we started with a delay that is time dependent. We started with a delay that is time dependent, and this is delay in reality. But it's very difficult to handle. So we replaced this time dependent delay by basically this formula here, in which your received signal is delayed with sort of a constant, and then it's multiplied by this guy here. Okay, so from now on, I am talking about this constant delay. Okay, we know its origins. Okay, but again, so basically we did all these steps in this lecture, basically, so that later we do not like think of this monster function alpha bar of t, the time-dependent delay. We will just talk about as if each path is associated with some constant delay. Okay, so this P of tau called the multipath intensity profile, and it tells you sort of the average power along the path with delay tau seconds. And it's typically a decreasing function of time. Okay, so this is P of tau, and so when you transmit your signal, right? So this is the transmitter, this is the receiver. If there is a line of sight between the transmitter and receiver, then basically the shortest delay between the transmitter and the receiver will be along the line of sight, and so this will be tau min. So this will be like, if this distance is d, so this will be like d over c. But you don't just get this path in a multipath environment. There are scatterers here and there, and your signal come like this, and so on. And so basically you get signals with more and more delay, and typically with increased delay, the average power along the path basically gets smaller and smaller, which so basically if the path is is being scattered off several times, basically in each time it loses some of its power. So you can intuitively have a feeling of why you have this decay here. And typically in receivers, the received power along, if it's basically below a certain threshold related to the noise floor of the receiver, typically it will be ignored, right? So perhaps, above some delay tau max, perhaps you are getting replicas of the transmitted signal, but if those replicas are with a power that is small, and by small I mean basically relative to the noise power in the receiver electronics, perhaps those are useless and you do not really need to consider them in your analysis or anything. So we typically assume that the delays, they go from some tau min to some tau max, and the difference between tau max and tau min is called the delay spread of the channel. So the width of the function P of tau is called the delay spread, if you want the full name, the multipath delay spread of the channel. Okay, so again, you transmit a signal. After some delay, you start getting copies of the transmitted signal at the receiver. Okay, and so you start getting signal, you start getting a significant signal, and then there is a point in time beyond which you may get a signal, but it's sort of like negligible. It's sort of indistinguishable from the noise in the receiver electronics. Okay, so you get significant powers along basically several paths with certain delays between tau min and tau max, and the basically the time difference between tau min and tau max is, you can think of it as the multipath delay spread of the channel. So this is the width of B of tau. So the width of the function that is called the multipath intensity profile, which is this function, the expectation of magnitude alpha of tau squared, basically the multipath intensity profile. Again, it's a function with a width, and this width is called the delay spread, and you can think of it as tau max minus tau min. Now, perhaps this is a digression, but it may actually serve us also when we talk later about things like the coherence, bandwidth of the channel, and so on. Why am I writing width between quotes, like width of a function? So the issue here is that there is no objective way to measure the width of a function, right? So if I give you a function like this, so this is a rectangular function. What is its width? Well, you can take the support of this rectangular pulse and say that this is the width. But what if the function is like this, and then rather than going to 0, it goes to a very, very small value, and it remains at this very small value forever, to the left and to the right. Okay, so here, if this is big T, you can say, width is T. Here, what do you say? If this is big T, if really the amplitude here is negligible, not 0, most likely you will also get it at big T, right? But what if the pulse is not rectangular, it's something like this? So what is the width of this pulse? So what you will see is that the concept of a width, again, is something that is inherently ambiguous, right? You need to choose. It's arbitrary. You may like to agree with the guys working in your field to have a certain definition, right? So for example, in electronics, like they measure the the 3 dB, so you go basically so this is normalized to be 1, they go to 1 over square root 2, and so this is like the width, right? For functions that cross 0, like the sinc function, so some people take the width to be the first, the null to null width. There are definitions of width that involve integrals, and those of you who took with me the signals and systems course in the previous semester, we studied the uncertainty principle in Fourier analysis, and it has a formula for the width in the time domain and the width in the frequency domain and so on. Okay, so moral of the story is the concept of a width of a function is not something that I can define objectively. We have a sense of it, but it should be defined by things that can be debated, right? It can be debated. I can say, why is this actually the width, or why is this the width? Actually, there is significant energy outside of the null to null width. Okay, so why should we ignore those side lobes and so on? You can always object to those choices. Okay, so take it easy. Okay, so width, that's the reason I'm writing here between quotes, because there is no rigorous definition, but there is a sense of a width, right? So again, let's go back to our particular subject. By width here, again, you transmit a signal. After some delay, you get the first copy, the first replica at the receiver, okay? And then after a while, the power of the received signal will become indistinguishable from noise, and so you basically take the longest delay minus the shortest delay, and this is sort of the width of basically the delay spread, or the width of the multipath intensity profile function. Any questions? Okay. Now, let's for a bit ignore time variations. So we are still setting like V equal to 0. And so the Doppler shift or Doppler frequency is equal to 0. And so we are basically in the land of standard LTI systems. And so an LTI system, it has a frequency response, which is given by this. It's simply, so basically this is just the CTFT integral. We are interested in studying the following correlation function. Okay, so if you take the Fourier transform of alpha of tau, so alpha of tau is like the inverse response, and its Fourier transform is the frequency response, and so it's the response to sinusoidal inputs, and we are interested in basically studying the correlation between the frequency response at the frequency f1 and at another frequency f2. So we will study the correlation. So the correlation in statistics is defined as you take the first guy, you take the conjugate, the complex conjugate of the second guy, and then you take the expectation. Okay, so this will be our interest. You know, what is the correlation between the frequency response at frequency f1 and that response at frequency f2? Now, when you study correlation, correlation may be high or may be low. Maybe it may be a high number, okay, or it may be close to 0. So a high correlation means what? It means that the channel response at frequency f1 and at frequency f2 are highly correlated. It means that if you transmit a signal at frequency f1 and you know, so basically part of the signal, some spectral component of the signal at frequency f1 and another spectral component at frequency f2, if the channel at f1 and f2 is highly correlated, then these two spectral components will encounter almost the same channel. Okay, so if the correlation is high, then again you transmit a signal, and this signal has a bandwidth. It has, you know, an infinitude of frequency components. If you consider the spectrum to be continuous function of f, there is a component at f1, there is a component at f2. If this correlation function is high, okay, and of course, how high is high? Again, I'm just talking here without being rigorous. But if the correlation is high, you know, in some sense, then basically it means that the components of the signal at f1 and f2, they encounter, they see almost the same channel response. But if the correlation is very tiny, perhaps 0, then basically the spectral components in the transmitted signal at f1 and f2, those encounter almost uncorrelated channels. And we will actually push uncorrelatedness and say they almost encounter independent channels. Okay, so again, the study of this function is to tell us what happens to signal. You know, our signals are never sinusoidal signals with particular frequency, right? They typically involve many, an infinitude actually of a continuous frequency variable, and basically the various frequencies will encounter various channel filter gains. You can think of h of f as like the signal is being filtered, and h of f is the frequency response of the filter. Now, basically, this filter is, you know, it may have a different response at frequency f1 and f2, and so the correlation is a measure of how similar or how different is the response at frequency f1 and f2. Now, studying this in a course like in signals and systems, basically, like things are deterministic. Now, I'm using the expectation operator. Why I'm using the expectation operator? Because, as I said, that the parameters that we saw in the received signal model are typically modeled as random variables. And so we typically, when we do the definitions, we take expectation. Okay, so let's be concrete. So this is h of f. okay, which is the CTFT of alpha of tau. Now, so this is modeled as a random variable. So this is a random variable, okay? And when we restore back our Doppler frequency, the theta will also be treated as a random variable. So now what is h of f1? H of f2 conjugate. So what will be this quantity here? So you need to have this integral at f1, and then you multiply it by the integral conjugated and at f2. And so basically this will be the double integral alpha tau, alpha conjugate tau prime, e to the minus I 2 pi f1 tau, e to the I, we need to conjugate to the bar I 2 pi f2 tau prime, and then we have d tau prime. Okay, so that's basically the product of this integral evaluated at f1 and evaluated at f2, and we need to conjugate. That's, you know, that's basically how we define correlation if we have complex valued signals. And again, if you do something like this, you know, this thing here, this alpha is actually, you know, is ever changing, and so we model it as a random variable, and so our focus will not just be this thing, it will be the expectation of h of f1, h conjugate of f2, and so this is the expectation of the double integral, okay? And if we assume that we can interchange the order of expectation and integration, this is not always valid, but if we, so assuming we can interchange the order of expectation and integration, then what you will do is that you will take the expectation and apply it to basically those guys. Expectation, alpha of tau, alpha conjugate of tau prime, and then e to the I 2 pi f2 tau prime minus I 2 pi f1 tau d tau d tau prime. Okay. So now we will get this expectation, and it looks horrible, and we need now to like basically make some assumptions so that we can move forward